Hello everyone, my name is Desh. In this video, I will explain our paper, Anchored Speech Recognition with Neural Transducers. Consider the following scenario. You have a smart assistant device, such as a smart speaker, and you want to give it an instruction. For example, Assistant, play my favorite song. But as you are giving this instruction, someone else starts talking in the background. Now, we want the device to only listen to what you said and ignore anyone else. How can we do this? One way is to check if the user has registered themselves with the device and use this registered speech, also called an enrollment utterance, to transcribe only the target speaker. A different yet related way is to store an embedding for the target speaker instead. While these are both good approaches, their main limitation is the need for the user to be enrolled with the device. This means that the method will not work if a new user, such as a guest, says the device-directed speech. An alternate strategy is that of anchored speech recognition with wake words. If we assume that the device-directed speech usually starts with a wake word segment, we can use this segment to extract the characteristics of the target user and then transcribe only the relevant speech in the mixture. This strategy has the dual advantages of being on the fly and also containing matched noise in the auxiliary segment, which cannot be guaranteed when using an enrollment utterance. In this paper, our objective is to build anchored speech recognition systems with neural transducers. Neural transducers have become the standard modeling choice for on-device ASR in the industry. Put very briefly, transducers are popular because they combine the streaming capabilities of CTC models and the conditional dependence of attention-based encoder-decoders. This is achieved by factoring the conditional likelihood into three parts: an encoder, a prediction network, and a joiner. The encoder processes input speech, and the prediction network autoregressively models the label sequence. The joiner combines these representations and outputs a distribution over the token vocabulary at each time step. We use two methods to perform anchored speech recognition with transducers. We add a tiny auxiliary network which consumes the wake word segment and generates a context embedding. This network is barely 1% of the original model size, and so the increase in total footprint is negligible. We use this context embedding as additional input to the encoder, with the hope that it learns to suppress background speech in its output representation. We also compute per frame similarity scores between the wake word segment and the mixed speech by computing embeddings for both. We use these scores to gauge the distribution predicted by the joiner. The idea is that if the current speaker is different from the main speaker, the similarity score is low and we boost the prediction of the blank token. To evaluate the performance of our proposed methods, we created synthetic mixtures from LibriSpeech with SNRs ranging between 1 and 20 decibel. We use the first 2 seconds of the utterance as the wake word segment. On the x-axis, we show 3 different evaluation conditions depending on when the background speaker starts speaking. On the y-axis, we have word error rates for the target utterance. First, we can see that there is no improvement in the 0% case. This is expected because the wake word segment in this case is also contaminated. However, when we do have a clean wake word, our methods show significant reduction in word error rate, namely 33.1% and 47.6% for the 50% and 100% shift conditions, respectively. If we consider an example from the 100% shift condition, we see that the base transducer model transcribed both the target speaker and the background speaker, which is undesirable. Our model, on the other hand, suppressed the background speech effectively using the anchor segment. We also looked at the similarity scores learned by the joiner gating method. Indeed, we found that these scores were higher for segments where the target speaker was speaking and lower for the background speech segments. Let us take a moment here to think about the context embedding. In order for the anchored speech recognition system to work well, The context embedding should extract only speaker-related information from the wake word segment and ignore any lexical information. However, our objective function at the moment does not enforce this requirement. We experimented with two auxiliary objectives to ensure that we disentangle style from content in the context embedding. Our first method is called feature reconstruction. In this, we use the context embedding along with the wake word text to reconstruct the wake word speech segment. The idea here is that the text would contain the content information, while the embedding would encode the style information to perform this reconstruction. To obtain frame-level content, we used keynotes obtained from an HMM-based forced aligner. We also experimented with a self-supervised learning objective that does not require an external HMM-based aligner. This is called variance-invariance covariance regularization, or VIC-reg. In this technique, we split all the wake word segments in the batch into two halves and obtain high-dimensional representations of each half. We then try to ensure that for any batch element, the representation from the left half is similar to that of the right half. This ensures that lexical content is ignored while computing these representations. The variance and covariance terms ensure that the representations do not collapse to a constant and that dimensions are decorrelated. Both the auxiliary objectives help improve our model. The biggest improvement was provided by VIC-reg on the 100% shift condition, where it improved the word error rate from 19.8 to 17.4%. Overall, our final model provides a 19.6% relative word error rate reduction over a base transducer trained without the anchor. If we plot the context embeddings and color them by speaker ID, we can immediately see that they group into speaker clusters. This validates our conjecture that the context embeddings capture speaker characteristics. In summary, we showed that using wake words to anchor a transducer-based ASR can be an effective approach to suppress background speech. We proposed to do this using the complementary techniques of encoder biasing and joiner gating. To ensure that content is disentangled from style, we proposed several auxiliary objectives. Please join us for our oral presentation at the session on multi-speaker ASR, or you can reach out to me by email. Thank you for listening.